Okay, let us now go to another type of circuit which is very important circuit in many applications, starting from a digital clock up to the computers, which is the RC circuit. In the previous circuits, we have studied combination between resistors and electromagnetic force device. The question now is, what will be the case if we have a combination between electromagnetic force device, resistors, and capacitors? We have seen that the capacitor can use to charge or can use to be charged by a battery, to have a charge on the place of the capacitor to introduce a potential difference equal to the potential difference of the battery. What will be the case if we have inserted a resistor in between the electromagnetic force device and the capacitor? That's what we are going to see in this slide. Effectively, the potential difference on the capacitor equals the value of the charge on the capacitor Q over the capacitance of the capacitor C. So this actually is the instantaneous potential at the capacitor at any moment. So assuming that we have an electromagnetic force device which has a potential E, and assuming that it is ideal EMF device, and we have a switch, we connect the switch at the point A. So we have a loop between the resistor, the capacitor, and the EMF device. When the loop is closed in this way, the EMF device will force charges to go through this closed loop. This forced charge will introduce a current, and this charge would be accumulated on the capacitor to charge the capacitor. So according to Kirchhoff voltage law, at any moment, the total potential in this closed loop should equal 0. And the total potential can be calculated as is the potential of the EMF device minus the voltage drop across the resistance, which equals I multiplied by R, minus the potential difference on the capacitor, which is Q over C. So we can say that E, the potential difference of the EMF device, minus the voltage drop across the resistance, minus I multiplied by R, minus the voltage across the capacitor, Q over C, equals 0. This is actually Kirchhoff voltage law for this circuit. And let us remember that I, the current, is actually the rate of change of the charge with respect to the time. So I is actually dq over dt. So we can replace this I by dq over dt. So in this case, this equation can be simplified as R multiplied by the current, which is dq over dt, plus q over c equals E, the potential of the EMF device. Now we have a differential equation for the charge with respect to the time. By solving this differential equation, we can find Q, the charge, as a function of time. By solving this differential equation, we find out Q equals C multiplied by the electric potential E multiplied by 1 minus e to the power minus t over rc. E is a natural number. It is 2.73 something. So it is a fixed constant number called natural number E. And t here is the time, which I have differentiated with respect to here. And r and c are the multiplication of the value r and c. So the charge on the capacitor in this circuit as a function of time is given by this equation. At time equals 0, there is no charge at all at the capacitor. So if you assume that the time equals 0, t equals 0, e to the power 0 is 1. So 1 minus 1 is 0. So the charge is 0 at time equals 0. So it starts from 0 charge and it is built up continuously. Assuming that the time is going to infinity after a very long time. After a very long time, e to the power minus something very large, it is nearly 0. So after a very long time, this term would be nearly 0. So in this case, the charge after a very long time would be Q equal C multiplied by the electric potential E, which actually the original value of the charging capacitor by the voltage source directly. So all the matter, the resistor has delayed the charging process such that it going from 0 to the final value continuously through the curve of this equation. That's what we are seeing here, charging capacitor. In particular, we want to know how the charge Q as a function of T on the capacitor plate and the potential difference on the plates V at the capacitor as a function T across the capacitor and the current I as a function of T in the circuit vary with time during the charging process. We begin with applying the loop rules of Kirchhoff voltage law to the circuit, traversing it clockwise from the negative terminal or to the battery, and we reach to what we have discussed. Okay? Now we have already obtained the result of a charge as a function of time. Once we obtain the charge as a function of time, we can find out the current by differentiating the charge with respect to the current with T. We can obtain the current I. If we have I, we can obtain the voltage or the potential difference at the resistance, I multiplied by R. If we have the potential at the source and the voltage drop at the resistance, we can obtain the voltage at the capacitor. Also, we can find the voltage at the capacitor from Q. Q over C will obtain the voltage at the capacitor. So, very simple. If I'm interested in finding out the potential difference at the capacitor as a function of the time from this equation, it would be Q over C. So the potential here would be E multiplied by 1 minus e to the power minus t over rc. That's what we are seeing. We have obtained the charge as a function of time. Q equals C multiplied by EMF multiplied by 1 minus e to the power minus t over rc. If I'm talking about the current, I'm talking about dq over dt. So by differentiating this equation with respect to the time, C multiplied by E multiplied by 1 is constant. So the differentiation would be 0. C multiplied by E multiplied by e to the power minus t over rc would be the differentiation of e to the power minus t over rc, which is minus 1 over rc, and we have already minus, so minus minus would be positive. So it would be E multiplied by C over rc multiplied by the exponential term. We have C in the numerator and C in the denominator, so we have E over R multiplied by e to the power minus t over RC. It means that the current at time equals 0, if we have t equals 0 as the starting point, this exponential term would be e to the power 0. Anything to the power 0 is 1. So at the starting point, the current E would be the potential difference E over the resistance. Actually, this is equivalent to if I'm connecting the potential difference to the resistance through a short circuit, direct. Okay? So at the starting point, all the voltage drop would be at the resistor and the current would be E over R. Then this current will decay exponentially, starting from the starting point E over R, will decay exponentially. At very large time, this exponential term e to the power minus infinity is 0. So at very large time, this exponential term would tends to 0. Okay? On the other hand, if I'm talking about the charge on the capacitor, we can find out at the initial time t equals 0, e to the power minus 0 is 1. So 1 minus 1 is 0. So at the initial point or the initial starting time, the total charge equals 0. When the time go very long time, this exponential term tends to 0. E to the power minus infinity is nearly 0. So the charge would be C multiplied by the electromagnetic force completely. So it will grow up exponentially to reach C multiplied by E, or C multiplied by the potential. And actually, the final value, as if I'm charging the capacitor directly from the electromagnetic force. If I connect the electromagnetic force to the capacitor, it will reach the charge is C multiplied by E. So the final value represent as there is no resistor, and the initial value represent as there is no capacitor. Once again, the final value represent as there is no resistor. The charge E multiplied by C equal the charge equal C multiplied by E. This the final value. The initial value represent as there is no capacitor, it is short circuit. So the current is E over R. On the other hand, if I'm talking about the voltage on the capacitor, it is Q over C. And already we have Q. So we just divide Q by C. So we find out the potential on the capacitor would be E multiplied by 1 minus e to the power minus t over RC. It means that the potential at the capacitor at the initial time or at the starting time would be 0, because once again at t equals 0, e to the power 0 is 1, 1 minus 1 is 0. Okay? At very long time, e to the power minus very large value is nearly 0. So at very long time, Vc would equal the same potential of the electromagnetic force device directly. So Vc final would be E. So effectively, the potential as a function of time will take the same shape of the charge as a function of time. It starts from 0 and grow up until it reaches the final value, and here the final value would be E. So Vc equal E as t tends to infinity. So effectively, a capacitor that is being charged initially acts as ordinary connecting wire. The starting point, it represents just simple wire. Relative to the charging current. A long time later, it acts as a broken wire or as an open circuit. So as the time is increased, this short circuit or this connected wire, it comes to be open wire or open circuit. So there is no current at time equals infinity. Hopefully it is clear. Okay. Let us go back to the equation of the charge as a function of time. We find that Q equal C multiplied by E multiplied by 1 minus e to the power minus t over RC. Let us stop at this combination RC. The product RC, first of all, it has dimension of time. How comes? This resistance and this capacitance. Alright? The units of the resistance is ohm. And actually it comes from volt over ampere. Okay? And the unit of the capacitor is farad. And it comes from coulomb per volt. So if we multiply 1 ohm by 1 farad, it will be volt over ampere multiplied by coulomb over volt. So this volt can go with this volt, so it will be coulomb per ampere. But actually the unit of ampere is the unit of the current, which is coulomb per second. So we can say that coulomb per ampere is coulomb per second. This coulomb is coulomb, so it is second. So the unit or the product RC has dimensions of time. So actually this is time over time. Okay, so the argument of the exponential here is dimensionless. Alright? This product is called the capacitive time constant. And usually we replace it with symbol tau. This symbol tau. Okay? So the product RC is called the capacitive time constant of the circuit, and it is represented by symbol tau. When the time t equal 1 tau, the value of the charge would be Q would be equals C multiplied by E multiplied by 1 minus T over tau, and we assume that T equals tau, so it is minus 1. 1 minus e to the power minus 1 is 0.63. So at just one time constant tau, the charge will be built up from 0 to 0.63 of its final value. In other words, during the first time constant tau, the charge has increased from 0 to around 63% of its final value, which is C multiplied by E. The charging times for RC circuits are often stated in terms of tau. For example, circuit with tau equal 1 microsecond charges quickly, but if we are talking about another circuit with tau 100 seconds, charge much more slowly. So effectively, by controlling the value of R and C, we control the rate of the charging. And actually, this point is the basic idea of any timer in electric circuits. And as I mentioned, this RC circuit is a basic circuit in digital clocks up to the computers. So everything need to, there is a clock inside it. There is RC circuit inside this device. Okay? Now let us assume that we have already charged the capacitor to its final value. So the potential at the capacitor is E. And then we have disconnected the switch from the point A to point B. Now the capacitor is already charged, and there is a potential difference on the capacitor equals E. Okay? And we have the resistor and we have this loop. Before disconnecting the switch from A to B, while the switch is still at A. The Kirchhoff voltage law was E minus I multiplied by R minus the potential at the capacitor equals 0. And because E and the voltage at the capacitor, both of them is E, so E minus E equals 0, so there is no current in this case. But when the switch has been converted to the terminal B, the situation is different. Now, the potential in this loop can be said as the potential at the capacitor VC plus the current in the resistor, or sorry, minus the current in the resistor equals 0 in this small loop. Okay? So, in this case, we are saying that the potential at the capacitor Q over C plus the voltage drop at the resistor R multiplied by I, and I here is replaced by dq over dt equals 0. This is a discharging equation. Okay? So, in this case, this is another differential equation for q as a function of t. We can solve it to obtain the charge at any time equals the starting charge at the time when I have switched the switch to B, which is Q naught. And this Q naught effectively depends on the potential difference V naught at the initial point. So Q naught equals C multiplied by V naught. So Q equals Q naught multiplied by the exponential term e to the power minus t over RC. So in this case, the capacitor was fully charged, and once it has been connected the switch to B, its charge would be flow through the resistor to discharge. So effectively, the positive charge here go through the resistor to be neutralized by the negative charge here. And because this is not an electromagnetic force device, there is nothing compensate the number of charges which pass from the positive side to the negative side to complete it inside the capacitor. This is not EMF device. So I have, for example, 10 positive charge here. One has passed from here to the 10 negative charge here. So one of the positive charge is neutralized with one of the negative charge. So the remaining here 9 and here 9. Then another one is going from here to here. So it would be 8, 8, and so on. There is nothing, there is no bump here inside the capacitor which can create new positive charge to make it continuous. So the charge will decay, and this decay is exponentially. Okay? Similarly, we can obtain the current. If we are talking about the current would be I equals dq over dt, the differentiation of the charge per time. So by differentiating this value with respect to the current, it would be q naught multiplied by minus 1 over RC multiplied by exponential term e to the power minus t over RC. So in this case, I would be minus Q naught over RC. And Q naught originally is C multiplied by V naught, the initial potential on the capacitor. So C multiplied by V naught over RC, and we can see that it is V naught over R. V naught over R. By replacing Q naught, C naught multiplied by V naught. So C by C would be V naught over R. Okay? So the initial current would be V naught over R, and it decreases exponentially until it reaches 0. Similarly, if I'm talking about the potential would be Q over C. So the potential will start from V naught and it will decay exponentially by factor e to the power minus t over RC. So in the case of this charging, everything is decaying. The charge is decaying, the current is decaying, and the potential across the capacitor is decaying. And all of them are decaying exponentially with the factor e to the power minus t over RC. Okay? And once again, RC is the time constant tau. And after 1 tau, the value will be decreased 0.63%, 0.63 of the original value. So after 1 tau, the value of the current or the value of the charge or the value of the voltage would be 1 minus 0.63. It means that it would be 0.27 of its original value. Okay?